Next, let's take a look of the potential method. For potential method, it is borrowed from a concept from physics where an object has different potential energy at different status. So consider there is a person standing over a cliff, and then what happens after he has dived into the sea? So if he is above at the top of this cliff, then this guy has a higher potential. And for this situation, if the person has already jumped or dived into the sea because it is at a lower level, then he will have a less potential. Now, in amortized analysis, the potential method, we can consider it as the complement of the accounting method. So this is actually my opinion. So what we are going to do here is we are going to fix a certain function. We call it a potential function. And this function is used to measure the bank savings that we have. And because it is representing the bank savings, we will make sure that this potential is always non-negative, which means that the bank will always have some money left there. It will not go bankrupt. And we will always need to follow this function for the bank savings. So once this function is fixed, then we can use it to calculate what is the amortized cost for each operation accordingly. So again, we will have bank savings and amortized costs as if we are doing the accounting method. But the difference here is in the accounting method, we are trying to fix the amortized cost first. And after that, we will show that the bank will always have enough to pay. And here we are doing the opposite. We will fix the bank so that the bank has always got enough money. And then after that, we will show what should be set for the amortized cost. So this is like we are doing whether fixing the amortized cost first or fixing the bank savings first. So let's have a closer look of how this method is operated. So let us use phi of I to represent the potential after the if operation. So what should the bank savings be when we are after operating the if operation? We let AI to stand for the actual cost of the if operation and alpha I to stand for the amortized cost of the if operation. Then we are going to set alpha I such that the following inequality is satisfied. So we hope alpha I plus whatever we can get from the bank, which is phi of I minus 1 minus phi of I. So let's say we have phi I minus 1 money in the bank before the operation, and then we hope that it will have phi of I money after the operation. So the amount of money that we can take from the bank to help the operation is phi I minus 1 minus phi of I. We hope that alpha of I plus whatever we can take from the bank is always enough, greater than or equal to enough to pay for the actual cost of the operation A of I. So this is very natural, right? So we have fixed already alpha I minus 1 and alpha I because we have fixed the potential function. And we know what is actually the actual cost of the if operation. And after that, based on this inequality, we know how to set for alpha of I. Now, if the potential phi of 0, which means that it is the initial potential energy, is equal to 0, then after any n operations, we will have the summation of amortized costs is equal to, so this is just writing down as alpha 1 plus alpha 2 up to alpha n. So this amortized cost of the first operation, second operation up to the nth operation. So this is total amortized cost. Using our relationship of how we set alpha I, we will know that this is greater than or equal to this following thing, A of I plus phi 1 minus phi 0. Look at this. So we have A of alpha of 1 is greater than or equal to a of 1 plus phi of 1 minus phi of 0. And similarly, alpha a2 is greater than or equal to a of 2 plus phi of 2 minus phi 1, and so on and so forth. Then, if we observe this, then we can simplify this by collecting all the a1 terms together, and then this phi k terms will get cancelled mostly, so that in the remaining part we will have phi of n minus phi of 0. Now, because phi of 0 is equal to 0, so this is gone, and somehow phi of n, it represents a potential, so we have a restriction that the potential of any operation, so with the potential after any operation is always non-negative, so this is something that is greater than or equal to 0. So in that case, the sum of this one is greater than or equal to a1 plus a2 up to an only, so it is the sum of the actual cost. So what does that mean? So if phi of 0 turns out to be equal to 0, then we have whatever that we want for the amortized cost. So because this is the only requirement, we just require that the sum of amortized cost is greater than or equal to the sum of actual cost. Okay, we have this idea, so let us put this idea into action. Let us revisit the superstack problem for the third time. Okay, so we are going to use the following potential function. We set phi to be equal to the number of items in the stack. So initially the stack is empty, so phi of 0 is equal to 0. So this is okay. So this is already something that is nice. Yeah, because we hope that phi of 0, it should be 0. So this is something that is already very nice. Now, let us consider what happens for the if operation. Now, the if operation could be a push, could be a pop, could be a super pop, but we don't care. So we will analyze each of the different scenarios and see what will happen and how do we set for the amortized cost of such an operation. Okay, now suppose that the if operation is a push. Now, when we push items into the stack, then the number of items before and the number of items after will have a difference of -1, because the number of items before will be smaller and the number of items after will be 1 greater than what the stack has before. So in that case, phi I minus 1 and then minus phi I is equal to -1. And then we also know that a of I, this is the push operation that we have, is equal to 1 for the actual cost. So in that case, we will need to set alpha I plus the change in this potential. So here, this is phi I minus 1 minus phi I. It turns out that it is a minus value. -1 is greater than or equal to 1. So if we set alpha I to be equal to 2, then each of these push operation works. Okay, so it satisfies this inequality. Now for pop, okay, in case of pop, phi I minus 1 minus phi of I is equal to 1. And on the other hand, the actual cost, so there is a table here, the actual cost, although it is actually equal to 1 or 2, whatever, it depends that we are having an empty stack or not. Okay, so our AI, so let's make it 2 here instead. So it is always 1 plus the number of removed items, so it is equal to 2 in the worst case. So in that case, we will need to have alpha I plus this one, whatever we get from the bank 1, is greater than or equal to 2. If this is the case, if alpha I plus 1 is greater than or equal to 2, then we can set alpha I to be 1 so that each of these pop operation works. And finally, for super pop. Now, for super pop, suppose that k is the number of items that is removed. So because of this, phi of I minus 1 minus phi of I, this is whatever we can get from the bank, is equal to k because we have k fewer items after that. So this one is equal to k. And alpha I is equal to 1 plus k as we know. So this is the actual cost. So for this case, we will need alpha I plus k, this is this part k, to be greater than or equal to 1 plus k. So here, alpha I, if we set it to be 1 for each super pop, it will work. Now notice that although super pop may be popping many items, the alpha I that we set here is independent of k. So this is something that is very nice. So in that case, no matter how many items are removed, we just always need to pay for a cost of 1 for each super pop. Okay, so that's for the super stack problem. So how about the binary counter? So for the binary counter here, we will use the following potential function. We will set phi, the potential function, to be equal to the number of bits 1 within the counter. Now initially, all the bits of the counter, they are zeros. So in that case, there is no 1 inside, so the potential is equal to 0. So it is something that is also very nice. Now, for the ith increment operation, suppose that there are k bits being flipped. Now, if we get a closer look when there are k bits flipped, so the last k minus 1 bits are flipped from 1 to 0. So we have k minus $1 that we can take. But on the other hand, the rightmost k bit, so the last bit that we are going to flip, the leftmost bit actually, that we are going to flip changes from 0 to 1. So we have to pay back $1 to invest a potential of 1 into this potential function. So altogether, the change of this potential function before minus after will be equal to k minus 2. On the other hand, because k bits are flipped, so the total cost will be equal to, the actual cost will be equal to k. So in order for this method to work, we will need to set alpha I plus k minus 2 to be greater than or equal to k. And then we see that by setting alpha I to be equal to 2 for each increment, it will work. And again, this alpha I is independent of k. So no matter how many bits are flipped, we just need to invest an amortized cost of 2 for each increment operation, and then we are done. Oh, this is a final remark or comparison between this accounting method and potential method. So accounting method is more intuitive as we can monitor how the money is flowing. We can see that how the difficult times are handled. So when we need a lot of money, where are the money that we can get from the bank? But the drawback for using this method here is that we need to come up with a good amortized cost scheme at the beginning, so that when we are trying to show that this works, then the bank really will have all the enough money to pay for each operation. So if we set the amortized cost to be something that is wrong, then after doing many steps for the analysis, suddenly we will find that the bank does not have enough money, so we have to restart everything again. On the other hand, for potential method, it is quite mechanical. What we need to do here is we just need to fix the potential function. Once the potential function is fixed, we can always analyze the amortized cost. So because we assume that the money in the bank has to be correct, so we just try to find out what should be the correct amortized cost to make this realizable. But on the other hand, the drawback here is that if we start with the bad potential function, we can have some very terrible amortized cost. So in all the problems that we have studied, we have already started with the best possible function that we can get. So in the end, we will find that the amortized cost looks very nice. On the other hand, if we start from a bad potential function, we may find that some operations we will have cost dependent on n. Then in that case, if it is like up to order n, then it will be really bad. So even if we have a correct analysis, then we will have a very bad amortized cost for the corresponding operation. So, but overall speaking, these two methods, it is like one is a complement of the other. So if you have somehow you have some idea of how the accounting method works, so basically you can immediately obtain a corresponding potential method for the analysis and vice versa.